Hi, I'm Alan Ross with APC Media. I'm the managing editor, and I am delighted to have as my guest Keith Redfearn. He is the CEO of Camlin Americas, and we're going to talk about Camlin Americas a little bit. But really, now that you're in this, and now that you've got a background in, I know you were with GE, I know you've been with Oracle, so you can solve all the world's problems, Keith, and that's what I expect you to do here. But we're going to narrow it down to the grid. So there are a whole bunch of challenges that we've got. Some of the solutions we have to challenges create further problems that we have to then address, which will probably create further challenges. But there's a lot going on in the grid right now, and I know as you look at a vision for Camlin Americas, you have to be looking at this grid that you're going to be able to implement that vision through. It's kind of the road that you have to build your house on, right?
Indeed.
I wasn't going to ask you about generation, but remind me to come back to that when we start talking about distributed energy resources, wind and solar, right? Because they in and themselves are a solution, but to one problem, decarbonization, they're also a problem, creating an inverter-based system. So we're going to talk about that. But from your perspective, looking at things from a reliability, resiliency standpoint, what are the challenges that you see of the grid?
I think first and foremost, Alan, is people still expect us to have a fully resilient grid. They expect when they switch the light on, the lights come on. And the grid is significantly more complex than it was when it was first designed. I think the deployment and accelerated deployment of distributed energy resources has, to the point you made earlier, definitely got upside. It helps us on that road to decarbonize, but it cannot afford to destabilize the grid. So technology-wise, if I looked 10, 12 years ago when smart grid first came about, it was in its infancy. I think there was a lot of good ideas, but the technology wasn't there to facilitate the deployment at scale of smart grid, technology thinking. 12 years later, we're now in a position where technology is no longer a limitation. It is actually a facilitation of what we need to do on the grid. So as we continue to deploy more distributed energy resources, whether that be at transmission level or whether that's distribution, more and more at distribution level, we have to understand what does it then take to control that grid to ensure it stays reliable and resilient. And I think that's one of the challenges that we in the industry as a vendor or as a technology provider have to work with utilities and other technology providers to overcome.
Grid. So I'm a reliability guy, and reliability is that an asset or a system works as it was designed for as long as it was designed without failure or disruption. That's reliability. That's one issue that we've got the grid has been fairly reliable from that perspective. We've had glitches here and there, right? We shut down all of Quebec and the northeast for only a day. Birth rate went up. It wasn't really a big problem. That was back in the 90s, I think. But the other one is, you mentioned it, resiliency. Resiliency is getting it back up when it goes down, usually due to natural disaster events, fire, hurricanes, tornadoes. The complexity of, we're right now, as we're talking, we're dealing with half of Florida didn't have power for a while, and it's still a mess down there because of a hurricane, right? Puerto Rico, its second hurricane in 5 years. And resiliency is making sure you bring stability back to the grid as quickly as possible so it again becomes reliable. That's a problem. That particular thing, you said technology is our friend now. How can technology help in those instances when you talk about natural disasters?
So clearly you still have to have the generation capacity to bring the system back up again, and whether that's large-scale fossil, whether that's nuclear, or whether that's an abundance of distributed energy resources, obviously we need to get that back up and running, connected to the grid. Now, that's not easy in those environments where you call it a black start. Effectively, the whole grid is sat down. Traditionally, you'd have to bring that up very slowly, one section at a time, to make sure you didn't overload generation or you didn't overload the equipment. If you do have a system of distributed energy resources set up in a microgrid, you can actually bring things up maybe a little bit more quickly. You're not relying on the full infrastructure, the transmission grid to come back up. You can bring small pockets of generation up, small communities back up over time, and then ultimately reconnect back to the grid. So there's a great example of where technology can facilitate a faster restoration without necessarily being inhibited by transmission.
Let's go to technology for a bit. So when you think about the technological advances, a lot of that has happened in the area of protection systems. Protection systems, relay networks are so much better than they were in the past. We're moving away from mechanical to solid state, electromechanical to solid state and everything. But talk a little bit about the technology as it relates to protection systems and anything else that is there today that wasn't there in the past. And I got another one for you, and how it relates to this thing that you just talked about, microgrids, because I think that's what we're going to have to do a lot more of in the future.
So originally protection systems are pretty straightforward. Now, don't ever say that to protection engineer, because you look at it, you look as if you're from another planet. But pretty straightforward. They were designed with a top-down approach: generation, transmission, distribution, all the way to the house.
Right.
Now, as you deploy other forms of generation, whether that be on the transmission grid or whether that be on generation, those standard power flows no longer apply in I guess throughout the day, depending on what your wind component is, depending on what your solar is. So typically those protection devices, the old mechanical relays were pretty straightforward. One set of settings, maybe two sets of settings. The modern technology allows each of those relays to have multiple settings to still be effective, irrespective of where power flow is coming from, irrespective of the generation mix on the grid. Those new digital devices give you a lot more flexibility and control over those adverse power flows, or those abnormal power flows, let me say. And that allows you to operate safely and effectively, either connected to the grid in isolation as part of a microgrid, or in other forms of network configuration. So there's a great example of how technology allows more flexibility on the grid.
Do you think microgrids are primarily, from a generation perspective, going to be DER, wind and solar? That's what powers a microgrid, and then you have to figure out you really don't have transmission as much as you go from generation to distribution. Is that what it's going to look like?
I think so, and I think you missed out an element there of storage. I think you can't really have transient generation without a good storage backup. Now, whether that's a battery or whether that's some kind of flywheel or whether that's pump storage, I think that always comes into the mix. But the ability to overcome the transient nature of wind, solar, whether that's a diesel generator or whether that's other form of renewable, it's that energy mix that is going to allow microgrids to really take off. And and some people, Alan, will say that at some point in time we've kind of gone back 100 years. Originally, all of these networks were small, isolated around the city. And now, 100 years later, we're starting to say, is it more cost effective to generate and consume locally and use a grid infrastructure as a backup or a secondary supply? So that's a quite interesting. Now, personally, I don't think we'll ever get to the ability or cost effective to scale as that being the normal operation. But for instance, if there's issues with the transmission grid, or even with some of the high voltage distribution network, can a community operate in a microgrid environment? And I look on the West Coast at the minute, some of those utilities really struggle with the fire season. Do they really have to turn off every little village, or can that village or town operate in a microgrid environment so safely, effectively, for a duration through a time of danger, and allow both the utility and the communities to benefit from an alternative form of generation?
There are no more experts out there. They're taking the rule of 80 or 85, number of years and age. Once you hit 80, you can retire, and they're taking the paycheck and leaving.
Yeah.
There's a lot of young people coming into it, but they're inheriting a very old aging grid. We're going to talk about that separately, but I want to go back to this topic of technology and reliability and resilience, and how the very technologies that that help in one area can hurt in another,
Yeah.
particularly DER. So FERC came out with the Federal Energy Regulatory Commission.
Yeah.
FERC said, hey, there's a new reg or an order coming out, what is that, the 2222?
22, yeah.
And it is specifically aimed at this whole new generation world of DER. What does that say and what does it mean?
So really what that means is, and I think there's a limit, I think it's 100 kilowatts, but basically anybody who generates 100 kilowatts can come onto the grid and contribute to, I guess, transactive energy framework. So they can sell into the grid, they can sell to another participant on the grid, but basically they have lowered significantly the size of generation required to participate commercially in an energy transaction. Now, from my perspective, that is fantastic. It allows us to further, deploy distributed generation on the grid and hit some of those decarbonization targets. But it also adds significant complexity to the grid. Because in that environment, there's an expectation that the grid capacity is infinite, that you can have as many connections. It doesn't matter what time of day, it doesn't matter what size, that the grid will sink in all of that generation and distribute it appropriately. Now, anybody who works on the grid understands that there's a finite capacity, there's a cost to generate, there's a cost to distribute, and trying to optimize that is extremely important. Now, that cannot be done manually. That has to be done more and more through technology, through understanding power flows, through understanding grid constraints, through understanding generation curtailment, to optimize that so you're maximizing the deployment of DER, which we all consider as a good thing, but also minimizing the instability potential impact on the grid. And that is a very, very difficult equation to solve, but it has to be solved in real time. That definitely you can plan ahead. You can say, if everything is perfect, this is what we expect it to be. But more and more with the diversity on the grid, there are real-time tools required to operate the grid to its, I'm going to say, its acceptable limits, but also to maximize that capacity and minimize curtailment.
You have mentioned something, and something I read, and it was about a greater operating control, insider control required in order to be able to do this. What do you mean by a greater operating control?
So I think in the past, typically the control systems, and I'm very familiar with ADMS, I've probably spent the last 25, 30 years running ADMS systems and deploying them with big customers. But typically they operate on a reactive basis. So the grid is operating, a control engineer might have a planned outage, you'll switch the network accordingly, but most cases, you can work around a planned outage. Unplanned outage is different. That's either a storm or equipment failure. And typically the control engineer has the ability to execute those operating plans in real time without having a major impact or effect on the grid, a negative impact. More and more moving forward, the grid is have to go, the operation of the grid is going to be semi-autonomous. And what I mean by that is the system is going to have to make its own mind up in real time based on better insight into the grid, better insight to assets, better insight to the capability and capacity of those assets. And the operator will only be working on the exception cases. So if the system cannot solve it, if the system cannot keep harmony, keep balance, minimize constraints, then the operator will come in and do further analysis. But I say within the next 5 to 10 years, even sooner, that those control systems are going to operate semi-autonomously on the grid. And they'll already do that now to, in FLISA scenarios where we're looking at an outage or we identify where the outage is, we will route around it where there's capabilities. But that kind of concept is becoming more and more inbuilt into the system when we talk about generation dispatches, DERs, etc.
So technology is making decisions that we used to use human brain power to make, and technology is that using. I hear a lot of people talk about AI and machine learning, and typically they mean machine learning. They don't. AI is different than machine learning. Machine learning is a subset of AI, but many times, you know, as engineers, you give me one data point and I can tell you one data point. You give me two and I can tell you a trend. You give me 100 and I can really give you with accuracy a trend. I can extrapolate a trend. We love extrapolation to trend. That's machine learning. You just give me data points, right? Where are we? So you're going to grade the entire grid in terms of use of AI and machine learning. Where really are we with that? Is it still nascent technology, or have you seen it working?
So if I look at the actual grid control, transmission distribution, we still rely on those real-time power flow systems. Yeah, I mean, that's still the core of the system. I think where I've seen machine learning become more and more applicable is as you get into the volume of the distribution grid and understand how smart meters deployed, are they on the right phase? You know, are you getting the right results from the field? Also, the use and deployment of field resources, is that optimum? Is there a better way to do it? And typically machine learning says, based on my past experience, I predict that this is what's going to happen based on the surrounding conditions. Now, is there a place for that in grid control? Absolutely. As the grid gets more complex and you understand, I'm currently at this situation, and over the next 8 hours, these things are going to change. What is the nominal or the optimal way to configure the grid to be able to accommodate what we think is going to happen on the grid? And I think machine learning has absolutely a part to play. But we're in very, very early days as far as that deployment across real grid at scale.
Is that why utilities are hiring more data scientists than they're hiring double E's? Is because they need a lot more data scientists to make this thing work. This is fascinating. I could talk to you all day about this, and I am, but I'm not going to do it in this session. But this has been an interview with Keith Redfearn. He is the new CEO of Camlin Americas, and we're going to get into Camlin and your role and what you see for Camlin in just a bit. So thank you for joining me, Keith.
Thank you very much, Alan. Appreciate it.